All right, good morning. Welcome to our morning session of the Summer Undergraduate Research Program 2020 Oral Project Summary Presentations. Our next presenter is Itohan Ero. She is a second-year computer science engineering student here at UCLA. And as you can see from her title slide, she worked in Professor Burton's lab, but I'm going to let her introduce herself and her lab. So let's give Itohan a big round of applause and please begin.
Yeah, so hey everyone, my name is Itohan Ero and I'm a rising sophomore studying computer science. And so this summer I worked with the Burton Research Group. They're in the Civil and Environmental Engineering Department. So my research is the development of a relational database to support post-earthquake building damage and recovery modeling. So I'm going to give you guys a little bit of background, then I'm going to go into my research overview, the role that I played, and my results thus far. So background. So the problem, after natural hazard events, specifically earthquakes, the functionality of affected buildings can be disrupted for extended periods of time. And so this leads to socioeconomic impacts such as housing shortage. And so the primary goal of the study is to develop computer models to simulate the post-earthquake recovery of buildings. So why? Why would we want to develop computer models of post-earthquake recovery? Well, number one, we want to investigate. We want to investigate how efficient policy level actions are at building resilience. So we look at pre-event mitigation measures. An example would be seismic retrofit, which is the remodeling of buildings to make it more resilient to earthquakes. We look at the policies that the stakeholders are making. Are they really benefiting the entire community? And lastly, this will look at measures that facilitate the timely completion of recovery, so that way people can get back into their houses as soon as possible. Two, we want to enable. We want to enable policymakers to explore different what-if scenarios. So in figure 1, you see a graph that shows different scenarios based on housing capacity and how they would affect the community. And number 3, we want to develop a resilience-based performance standards for buildings and lifeline systems in communities. So my research. My focus is enhancing the resilience of communities to earthquakes. So in particular, I focus on the South Napa earthquake. So on August 24th, 2014, a 6.0 South Napa earthquake occurred, and more than 2,000 structures were damaged. So this led to a great economic loss with about 500 million to 1 billion. So the data that we have, in figure 2, you can see some of the affected buildings that were affected in Napa. And so we gathered about 3,600 damaged buildings. And we have information based on location, the occupancy type, repair time, and more on each building. So here you see the spreadsheet that includes all the different attributes of the data that I will be putting into a relational database. So previous research. I mentioned models at the very beginning. So before they created stochastic process models, and stochastic just meaning a random probability. And so these were used to replicate the recovery of damaged building stock. And so in figure 4, you can see a recovery model validation was used based off data from past earthquakes. And so they built this data using a random forest regression tree, which you can see towards the right. And so this basically updates, well, it doesn't update, but it's based on certain criteria. So this specific stochastic process model is static and it's hard to apply to other future earthquakes. And another factor is that it doesn't update when new data is retrieved. So my current research. The Burton Research Group has developed a Bayesian parameter estimation framework for post-earthquake recovery modeling. And so this one is different from the stochastic process model because it updates. It uses Bayesian statistics to update based on uncertain events and when new information is presented. So my goal is, in order to increase the applicability of this framework, is to develop a relational database to manage the large data set of building damage and recovery parameters. So my role. My main task, just like I said before, is to develop a relational database. And so I've done this using MySQL. And so why would you want a relational database? So in this particular database, the data contained will be useful for calibrating and validating the recovery models. It also improves the readability of the data compared to spreadsheets. It provides an effective tool to reduce data redundancy and increase resource efficiency. And lastly, you could integrate different types of data from different sources seamlessly. So some of my other tasks just include writing Python code to enable visualization, developing a Python web scraping tool to pull data from websites, entering the current data set into the database, and collecting and processing the missing data from the current data set. So the results that I've got thus far. So pertaining to the database, I'm gonna give you guys a little bit of background when I keep using the word relational database. A relational database is a series of interrelated tables which are linked through shared fields, which are called keys. And so a primary key is a unique identifier for each table. And a foreign key is an identifier that links different tables together. And so an attribute would just be a column or factor. Like I mentioned that we're taking things like building height, building age, these are attributes. And so a schema is the combination of the tables, the attributes, and the relationships. And so this serves as the backbone to the database. So how did I go about this? Well, first off, I used data from the NAPA dataset that my lab compiled. Then my lab developed a database schema for the database. And then I went in on MySQL and I started coding and developing the schema and uploading data. Then I built a Python scraping tool to extract information from the web to add to the dataset. And lastly, what I'll be doing in upcoming weeks, I'll be analyzing this data using Jupyter and Python. So in figure 6, this is a schema of the relational database that the Burton Research Group developed. And so in the green rows, these are the primary keys that I mentioned. And so they specify the unique part of each table. So for example, based on the earthquake property, each earthquake ID specifies a certain earthquake. Each permit ID specifies a specific permit. And so the way they wanted to relate it are through the blue keys. And so this was the structure that I based my database on. So then I went in on MySQL and I developed a schema. So this is the visual component of what it looks like behind the code, but this was where I typed in the specific types. If it's a character, integer, a long int, a long char, this is where I specified that. And so the code to the schema is shown right here. This is where I was able to implement the backbone of the database before entering information. So this is part of our database where I got to start implementing information. So in figure 10, this is the permit information table. So this shows different permits, the date that they were applied, the date that they were received. Figure 11 shows a shaking intensity table. Figure 12 shows the building information. So building names, building IDs, building age. And figure 13 shows an earthquake information table. So all of these tables are interrelated based on the schema that I showed you before. And this is going to allow us to analyze the data in ways that you won't be able to just on a spreadsheet. You can call different data together based on certain criteria. And once again, this isn't the full database. This is only parts of it. So the Python web scraping tool. So what is web scraping? So with the web scraping, first off, you have a web crawler. And so that uses AI to search the internet for certain things that you're searching for. And then you have the web scraper. And so this is a tool that extracts the data from the web page. And that is what I created. So the goal was to extract information from the earthquake engineering research sites. And so to figure out which ones I needed, I quantified the missing data. And so in this graph here, you can see that we were missing the number of units, we were missing the site class. So these are things that we wanted to go back to the permit sites and extract this information to add to the database. So in this slide here, you see some of the web scraping code that I used. The left-hand side, figure 14 shows some of the code that pulled from the building site. And figure 15 shows the code that pulled from the permit site. So these were adapted based on the website features. So for the building site, the site had images for each building. And on the right-hand side, it had a long list of factors. And so the code that I wrote pulled from each of the buildings the information we needed. And so it had to be able to run through all of the 3,600 images we had. And so this is a part of the CSV file that was downloaded after scraping all the tools. scraping all the information. So the tool was also adapted to be used on the permit site. And so this one was a little bit more complicated. You had to search up each of the addresses here, and then you had to iterate through each of the resulting tables and only pick out the ones that represented earthquakes. And as you can see here, that's represented with the EQ. So the code would find all the EQ permits and extract information from there. So here you see a CSV file that was extracted from that site. So I pulled information such as a short description, the applied date, the address. So this is also a very long CSV file, which is like an Excel spreadsheet that can't be modified. And this will be implemented or input into the database. So in conclusion, the relational database will increase the effectiveness of the Bayesian parameter estimation framework. And this will help calibrate and validate post-earthquake recovery models. And so this will advance our ability to mitigate the cumulative adverse effects of major earthquakes on our communities. So these are some of the references that I used. I want to thank my lab, the SURP program, for all the materials and help that they provided me. And thank you guys for listening to my presentation. Oh yeah, are there any questions you guys have?